Oh, hello. In this module, we'd like to discuss monosaccharides, or single units, which we call carbohydrates. Of course, today with all the diets, Atkins diet, South Beach, North Beach, East Beach, West Beach, we call them carbs or sugars. And the basic formula for a carbohydrate or a carb or a sugar is carbon and then some number of units of water. So when we take a look at our structure, we're going to make sure that we have twice as many hydrogens as oxygens. Now we don't have nitrogen, fluorine, sulfur. We only have carbon, and then we have units of H2Os. Here's a backbone making up one of these monosaccharides, or our simple carbohydrate or sugar. I have 6 carbons in a row, and these tend to be aldehydes, and this is an aldehyde, or you can go ahead and do a carbon-oxygen double bond here and have a ketone. So we've got ourselves an aldehyde at the moment, 6 carbons. The functional group aldehyde is shown at the top. Down at the bottom, we have a carbon which is always going to have CH2OH. Carbon, 2 hydrogens, and an OH. Now that brings us to the water units already. I have up on the board water units. HOH, so here's a water unit. HOH, so there's a water unit. So when I fill in these little lines that I've set this up for with H's and OH's, I had better put water units, have the correct stoichiometry there, otherwise I will not have a carbohydrate. Now, it turns out that this carbon is very important to us. We use it for labeling purposes. It's not this carbon, but it's this one, the next carbon up. I'm going to put an asterisk by it. That asterisk will turn out to be very special in a couple of moments. Now that's going to have OH on one side and an H on the other. And I'll work my way up. And I'm just making this up as I go. I'm going to put an OH on one side and an H on the other side, and I'm going to choose to put the OH on this side and an H on this side. I'll stick with that. OH on the left, H on the right, and now I'll switch things up and put the OH on the right and an H on the left. I have complete confidence that I've done this correctly, and it is a sugar, some molecule that can be classified as a sugar, and it'll have some common name like glucose or galactose. There it is. 6 carbons, aldehyde, and a sugar or a carbohydrate. That brings us to the name of this. A general name, not its common name that people would label it as, is aldo, which is for the aldehyde up at the top. 6 carbons, prefix for 6, hex. So this is an aldohex. And because it's a carbohydrate, it has the correct formula and structure. It has the OSE ending. Aldehyde, 6 carbons, sugar like glucose or table sugars called sucrose. This is an aldohexose. Back to this carbon right here. I put an asterisk and said, it's an important one, do it in just a moment. Well, here's that moment. I chose, because I just made up my mind, to put the OH group on the right. I could have put it on the left. If the OH group is on the left, and again, not the bottom carbon, this doesn't have the same configuration. This has 2 hydrogens and an OH. This one doesn't have 2 hydrogens. It has 1 hydrogen and an OH, and then a group on the bottom and a group on the top. This one here has the OH on the right. If I had put it on the left, it would be different. If I put it on the left, I would call it an L for a left-handed sugar. That's not the case. I didn't put it on the left, I put it on the right. And therefore, I could call it R for a right-handed sugar. But that would be too easy. That would be too straightforward. We're not allowed to do straightforward in chemistry, so we can't use R. We're going to cross that out and say it's D, which translates from dextro, or right-handed. So I made a point of saying we don't have left and right exactly. We have L left and D right for dextro. So this is a D sugar, and here's the mouthful. Because I put the OH group on the right on this second carbon up, it's a D-aldohexose. Now, I'm going to put stars on the other carbons on the way up and tell you why. These stars or asterisks mean that these carbons are special. We call them chiral. Chiral, as though it's pronounced without the H, chiral. And a chiral carbon has 2 criteria. Number 1, We know that carbon needs 4 bonds, but carbon doesn't have to have 4 singles. For example, in the aldehyde, this carbon has 4 bonds, single, single, but a double. A chiral carbon has 4 single bonds, as all these do that I've labeled with asterisk. The other criteria is they have to have 4 different groups. Now, I didn't write 4 different atoms attached to it, I wrote groups. For example, this carbon has a group that's a hydrogen. Carbon has a group that's an OH attached to it. The third group that I'm going to identify is going to be CH2OH down at the bottom. And the fourth group is big hunkin' piece. That whole thing up at the top. Not the first atom out. It's not fair to say this is a carbon, that's a carbon, they're the same. This group is very small, CH2OH, and this is huge. So this carbon has 4 different groups, so it's chiral. This has 4 different groups, chiral. 4 different groups, chiral. 4 different groups, chiral. Top one, not chiral. 3 groups because of the double bond. This bottom one's never chiral because it has 2 hydrogens, not different groups. Why does this matter? Inside your body, you have huge molecules that we call enzymes or macromolecules, and they offer some type of function, chemistry function, and they're all set up to receive a molecule. Now let me go ahead and make a little pattern here and write 3 circles here. Like this molecule is going to accept another molecule here, and it's expecting some atoms to land here. It's expecting a red atom to land here, a blue atom to land here, and a white atom to land here off of a molecule. Now, of course, it's not red, white, and blue. It's going to be some type of carbon or nitrogen or fluorine or sulfur or nitrogen, some type of group. But I'm set up to do this with models. Here comes a molecule of interest. I have red, blue, and white all set to go into position, and I'm holding it by this whatever color green this is. So here comes the molecule. It's all set. It lands where it's supposed to, and function happens. Maybe it's the job of this big molecule that I have sketched out on the board to do things like break some bonds, like, hey, let's go ahead and digest this molecule and break it up into pieces. Here's the same molecule. Red goes where red should, blue goes where blue should, and white. But if I switch the sides on this, I'm going to switch white and blue. It's not the correct configuration, and function will not happen. I'm holding it by this green again. I'll put red in the correct place, and they don't match up. It's the wrong-handed. It's like gloves. It's like trying to put a right-handed glove on a left hand. Somewhere there's an O.J. Simpson joke in there. Let's see. Let me put these molecules back together and show you what I've got. Something like right and left-handed. There's a mirror reflecting this molecule onto this molecule. The blues are far away from each other, the whites are close, and the reds are close. They're not the same molecule. When I try and overlap them, I'll put the whites on top of the whites, and the red and the blue are different. There's nothing I can do. I can't do anything about it. In order to get them to be the same, I'd have to undo 2 bonds and switch them, and then they'd be the same. So chiral